Alright, today we're looking at waves. So let's look at the definition of a wave. Waves are a type of periodic motion that carry energy from place to place. Waves undergo simple harmonic motion, which means they repeat themselves. There are two types of waves that we're going to look at. Longitudinal waves, where particles move back and forth in the direction of the wave, and transverse waves. Particles move perpendicular to the wave. It's going to be easier to show you than to tell you. So here's the difference between a transverse and a longitudinal wave. You'll notice that the coils on the slinky in the transverse waves are moving up and down while the wave moves to the right. And then with the longitudinal waves, you'll notice that the coils go left and right as the wave moves to the right. So transverse means the particles are moving perpendicular, and longitudinal means the particles are moving in the same direction. So this is what it looks like with individual particles. You'll notice that the wave looks like it's moving across, whereas the particles are just moving back and forth. No one particle is moving all the way across the wave. The particles are just moving back and forth, and the wave itself is what's going from left to right. Let's look at the parts of a wave. The top of the wave is called the crest, the bottom of the wave is called the trough. The amplitude is the distance from the midpoint to either the crest or the trough. Wavelength is the distance from crest to crest, trough to trough, or any two recurring points on the cycle. What I mean by that is if I'm at this point going downward, this whole thing is a wave until I get back to that point moving downward. So that's one complete cycle, and wavelength will be that distance from the beginning of the cycle to the end of the cycle. Now that distance is the same as the distance from crest to crest, and it's the same as the distance from trough to trough. Same as the distance from this point in the cycle to this point in the cycle. So you can get wavelength any one of those waves. A wave like the one pictured here can be tracked and recorded using an oscilloscope. Okay, that's important. That's going to be on your quiz on how to record a wave. It's an oscilloscope. So wave speed, frequency, and wavelength. This is going to be the calculation part of waves. All those definitions you're going to need, so make sure you go back, write them down, screenshot it, however you want to do it. V is going to be wave speed, which makes sense because we usually use V for velocity, so you can think of it as velocity. F is frequency, usually measured in hertz, and lambda is wavelength. That funny looking symbol there looks like an upside down Y. It's called lambda, and that represents wavelength in meters. Here's an example. Ocean waves are observed traveling along the water's surface during a developing storm. A Coast Guard weather station observes that there's a horizontal distance of 10 meters between each crest. The waves splash onto the station once every 5 seconds. Determine the speed of these waves. Now we'll see that V equals F lambda is what we're going to use. It's asking for the speed of the waves, so that is going to be V. Speed of the waves, V. It gives us the frequency. It says it splashes into the station once every 5 seconds. So if you remember from simple harmonic motion, the number of cycles divided by the time it takes for those cycles gives me frequency. So I have 1 over 5 hertz. And lambda is 10 meters because he measured the horizontal distance between each crest, which is your wavelength. So V is going to be F lambda, which is 1/5 times 10, which means V is going to be 2 meters per second. Now let's take a look at sound waves. It's a mechanical wave, which means it needs a medium such as air, water, or solid to travel through. So not only are they mechanical waves, they are longitudinal, which means their molecules oscillate parallel to the direction of propagation and remain in the same position. Same thing we talked about earlier. They move back and forth in the direction of the wave. The two qualities of sound are loudness and pitch. Now, loudness is going to be affected by amplitude, which is what we saw earlier when we looked at parts of the wave, and it's measured in decibels, dB. Pitch is measured by frequency, which is measured in hertz. So the frequency of the wave, the number of times it oscillates per second, gives you frequency. So the more frequent the wave oscillates in the same amount of time, the higher the frequency, which means the higher the pitch. Humans can only hear frequencies between 20 hertz and 20,000 hertz. Above this frequency is called ultrasound. So the same ultrasound that they use to see babies in the womb just means that they're using sound to get a picture, and that sound cannot be heard because it's over 20,000 hertz. All sound waves travel with the same velocity in air. It's approximately 340 meters per second. That's what we're going to use. I've seen books and sources say that it's 343, and then you'll find other sources that have even more accurate decimals than that. But for the sake of what we're doing, we're just going to call it 340. And last little tidbit we're going to learn about sound is that white noise is an even mixture of all sound frequencies. All right, here's our first example. A pianist plays a note that has an approximate wavelength of 1.299. Now remember, sound is a wave, so the V equals F lambda is going to apply to this. So wavelength is lambda is 1.299. If the speed of sound in air at this location is 340 meters per second, which piano key represents the frequency of the sound wave produced? Now V and lambda are given, and we're looking for frequency, so we set it up. 340 equals F times 1.299. If I'm trying to find F, I'm going to divide both sides by 1.299. So 340 divided by 1.299 is 261.7 hertz. So if we look at all our frequencies, the closest one to this is the 261.6. So we're just going to call that note C.